A very good morning, ladies and gentlemen. Now, let us start our second day of GYAN, concrete microstructure characterization, for which we are eagerly waiting to hear from Chief Resource Person, Professor Narayanan Neithalath, sir, Arizona State University, United States of America. It's over to you, sir.
Okay. Good morning, everyone. Can you hear me? So, welcome. Happy to know that you all survived day one, right? Okay. Hopefully, this will be an easier day. Dr. Das won't keep you till 8 o'clock tonight. We'll see. Okay. So we'll start from where we stopped in the last lecture. So we talked about cements, the basic reactions that happen when cement reacts with water, right? And most of the things that you're aware of. Today we'll go a little more deeper into what exactly causes the microstructure to form the way that you would see for most types of concrete. Okay, in the afternoon session when I talk about ultra high performance concrete as part of the conference, I'll give you some more flavor on how particles pack and things like that, but I'll give you an introduction also now. So our idea now, remember from yesterday, was about cements, right? I never told you anything about concretes. All we did was how cement reacts with water, and I even gave you an example of taking 1 grain of cement, 10-15 microns, putting it in water, which I called infinite dilution. Remember that? And then making it react and watching how reaction happens, which is the cause of microstructure of concrete. Today we'll extend it slightly and give you basically again a little theory, and some of you, if you are doing PhD, if you're faculty, you might like it because it opens the doors as to why it is happening, right? In research we have 5 W's, right? Why, what, where, which, when. Right? We're trying to, and in this, so these are 5 questions that you always want to answer, 5 W's that you always want to answer. But why is more important for research, because the question of why leads to further discovery. Why does this happen? If you know why that happens, right? Doctors, okay, you have a fever. Doctor gives you a Tylenol. You don't have to know why he gave you Tylenol, right? But he has to know why he gave you that specific medicine for this disease. And if that medicine didn't solve your problem, he should know why that didn't solve the problem so that he can give you another one. See that? So for progress, the question of why is important. Now, if you're interested only in making a big concrete slab or a roof or a concrete foundation or build a concrete house, forget about why. How do you do it? Show me where can you do it, how do you do it, when you will do it, which place you, right? Questions are over. You don't need to. You don't need to do that in that sense. Now, oops, where did I go? Oh, it's here.
Slightly loose.
Okay. Good. Go to the previous slide.
71, right? I have to close it and I have to remove.
Okay. Good. Thank you. Go to the previous one. Okay. So we are looking at why things happen. So if you are just constructing something, you may not need this why. But if you are in the area of research, if you're teaching, if you want to know these processes, so we'll spend some time doing it. All of you good with that? You have no complaints, right? Again, if you think a certain topic, no, this we all know, we don't need it, let me know. We can move on to the next one so that we can do it faster. Okay, and ask me questions also today so that I know you're not sleeping. You can sleep with eyes open, you know that, right? Okay. So, remember yesterday I talked to you about 3 different things. Changes in matter, changes in energy, and changes in speed. Right? So any reaction will result in change in mass, change in matter. Any reaction will result in change in energy, and any reaction will require a certain speed for it to proceed. So three different things. And these three different aspects combined causes new phases to form. Now remember, what do you have basically in your cement grain? What are the four phases in your cement grain? C3S, C2S, C3A, C4AF. Do you want those four things to show up exactly like that in your concrete? Is there any use? This is like asking, I put salt in my dish, do you want the grain of salt in your dish again? You want the salt to have assimilated through the dish to give you the taste that you want, right? Similarly, you want the calcium and the silica and the aluminates to be spread out throughout your system in a different form to give you the properties that you want in your concrete. So your C3A, and remember I talked to you about dissolution and precipitation yesterday. Things have to dissolve, things have to precipitate back. What precipitates back is not what it came from. It's a different species, right? So your phase has been transformed. Get that? You're not getting the same phase that you started off with. You're getting a transformed phase. That phase transformation involves two different things. The first phase, the first process is called nucleation. And yesterday I gave you an example of cheating the system, right? And what was the example that I used for that? Use of limestone. Limestone cheats the system by letting cement hydration products nucleate on limestone. So nucleation is the first process in phase transformation. And then when things nucleate, it's not just enough to form that nucleus and stay there. That nucleus has to grow into the reaction products that you want, right? So nucleation and growth. This is standard chemical equilibrium story. You have to have nucleation, you have to have growth. So those are the two different aspects. Okay, so there are two types of nucleation, homogeneous nucleation and heterogeneous nucleation. Just again some theory, and I'll show you examples in cement where this happens. Homogeneous nucleation meaning everything is so homogeneous. I have a grain of cement, I have water around, you have ions released from the cement to the water, the solution gets saturated. When the solution gets saturated, ions will have to precipitate back, right? That's the story, that's what it is. But in homogeneous nucleation, it is precipitating in a solution. Realistically, for reactions to happen, I told you yesterday, calcium hydroxide will need some surfaces to form, right? So you need the limestone, very small particles of limestone acts as nucleation sites, and calcium hydroxide will form on top of that, right? But the simpler case to study is when I don't have anything to form on, it's just one big dilute solution, I have a grain, and randomly the nucleus forms in the solution. Get that? Is the idea clear? And that is called homogeneous nucleation. So, it depends on the internal energy of system. That internal energy is called Gibbs free energy. These are thermodynamic terms. And entropy or disorder of the system. Enthalpy and entropy, all of you are familiar with, right? Entropy is the degree of randomness in the system. Enthalpy is the internal energy of the system, how much energy the system has. You heat it, enthalpy goes up. You heat it, the molecules start running around because they have more energy. Entropy also goes up, right? So enthalpy and entropy. Now, you give a system certain energy. Classic example is heating a concrete for the reaction products to form faster. All of us do that, right? If you're doing precast concrete, they heat the concrete to 70 or 80 degrees Celsius for the reaction to form faster, for the cement hydration to happen faster. So basically what are you doing? You're giving more enthalpy to the system. But there is an enthalpy penalty also. You have to give some energy from outside to the system. It's like a bank, especially banks in India. You put money in the bank. What happens if you don't put in a minimum balance? What happens? It will charge you a service charge, right? Same thing. The system is telling you, okay, you want me to go faster, I need a service charge to go faster. And you give me 200 rupees or energy equal to 200 rupees, I'll give you only the product for 150 rupees back because 50 rupees is my service charge, right? So systems, all systems, anytime you try to accelerate a process, you end up with an enthalpy penalty. You won't get all you gave back, all you gave to the system. You see that? So again, each example is to think about banks with no minimum balance that you have in it. So they'll take your service charge. Enthalpy penalty, system is taking your service charge. So we'll come back to that in the process of product formation. So you have a liquid, you have a solid. Now let's take a simple case, and I'll do some math here if you're interested. Simple case. Let's take a spherical particle. Okay? Volume of spherical particle. All of you good with that? I've not made any mathematical errors here, right? So that's your volume of your particle. Now, the change in free energy, this is very easy to understand. I have a particle that is spherical in a big system. That particle is reacting, which means its energy is changing, right? When I'm standing here doing nothing, I have no change in energy. But when I'm walking around, when I'm running, when I'm reacting, I have change in energy, right? That change in energy for a particle, now think about this, it's very simple. You have a solid phase and a liquid phase and an interface between the solid and the liquid, right? A boundary between the solid and liquid. So you have to have your free energy as two different components. One is a free energy difference between solid and liquid. The solid and liquid does not have the same free energy, right? Solid has a lower state of energy because it has a specific shape. Liquid has a higher energy. So there's a free energy difference between solid and liquid. Classic example, two of you might be sitting close to each other. You might be even touching each other. Do you have the same energy? No. One of you might be very sleepy, the other might be very excited, right? So the free energy of any system will be different based on the location of the system that you're looking at. Okay? So that's a free energy difference. And that free energy difference is nothing but the volume of the solid times a volume free energy, because solid has a certain volume. We call it delta GV, the volume free energy. And then energy created as a result of interface, 4 pi r square is the surface area of that sphere times gamma, which is surface free energy. So you have these two free energies. My actual free energy is the sum of those two free energies. And then if I plot free energy change as a function of size of the atom. Now, I have a small nucleus that I have now, right? When more and more products form, how does that nucleus grow? It grows. But I told you yesterday about the idea that you cannot go down to the lower state of energy without overcoming a energy barrier, right? So basically, this little thing in a pool, in an ocean of water, wants to react. Reaction causes a new product, but the nature is saying you can't be so lazy. If you want to go down to your lower state of energy, you have to overcome an energy barrier. Which means, in simple language, I have a very small nucleus, and if that nucleus wants to grow into a reaction product, all it takes is to get to a certain size beyond which it can grow. Until you get to a certain size, you need somebody to help you, like little kids, right? When you're 13, 14, 15, they run away from home and they do their own things, but until then they need the parent to supply them everything, right? Very same idea, you need a certain activation energy, certain barrier to overcome. So if I plot the volume free energy, you see that here it's negative because the volume of the initial product is shrinking, right? Because new products are forming. The initial grain is shrinking. All of you get the idea? So that's negative. The surface area is positive because more and more surface area is being created because of the reaction. See that? So one is positive, the other is negative, and if I add that, I get this green dotted line, which is my free energy. This is where, not just cement and concrete microstructure, any reaction follows the sequence. And cement and concrete also is not very different. So you have this curve, and you see a peak in that curve, a peak value in that curve, until which the free energy change or rate of change of free energy is positive. See that that's going up? You need that delta G, that's called the critical free energy change or the activation free energy. You need that free energy to form a stable nucleus. If the reaction did not give you that energy, what will happen? Nothing will form, the reaction will stop there. Okay, that's the importance of a critical size of a nucleus, which we'll see. For basically, for example, I'll give you a simple example. When you have calcium hydroxide that has to nucleate and form, you know the shape of calcium hydroxide, right? Hexagonal plates. Hexagonal plates of calcium hydroxide, when you have to have that formed, it starts as a nucleus and it has to grow to a certain size defined by this energy. So basically, whatever is this radius in this x-axis, it has to get that energy or that radius for it to continue growth, and then only free energy will decrease. For formation of molecules, do you want free energy to increase or decrease? Eventually free energy should decrease because stability is lower energy, right? Only lower energy. Sleeping is lower energy than standing up and running around. Sleeping is a more stable state than running around. That doesn't mean you should sleep all the time, but it's a more stable state. Okay, is this idea clear? Again, if you want to do theory and proof, this will be a nice example, and for people who are doing research and on new materials, it might be good to find out. Again, you need some thermodynamic calculations, you need some mass balance equations to do that, but these are nice calculations to figure out why something is forming in your system. Oh, I have needles of ettringite, and after some time I don't see ettringite, they transform to monosulfate. Why does that happen, right? Ettringite particles many of the times doesn't get to a critical size. They have to transform to something else. They can't grow on their own as ettringite. Simple, right? Now, you see ettringite in certain cases when you have additional what? You see a lot of ettringite when you have additional what in your system? Additional sulfates. Why? Because the extra sulfate is providing the free energy required for it to get to a critical size. And then therefore ettringite stays as ettringite. If not, ettringite transforms to monosulfate. Now, in that equation right there, in that simple equation, is a reason for why ettringite doesn't stay ettringite. If you have a sulfate deficient system. If you have a sulfate rich system, ettringite stays on. If you have a sulfate deficient system, ettringite transforms to monosulfate, which is what you actually want because ettringite is expansive, problematic. But there are certain times when you like ettringite. Do you know when that is? You want ettringite. You would be okay with ettringite. If you put in a lot of aluminates, if your sulfate alumina ratio is fairly low, with a lot of aluminates and little of sulfates, you will get a lot of ettringite, right? But early age ettringite, is early age ettringite a problem? No. If volume change happens early ages, am I worried? No. What I'm worried is volume change happening later on. So you don't want ettringite later on, but you're okay with ettringite early on. And for some systems, you prefer to have more ettringite early on. If I want very high early strength, I'm okay with ettringite early on, provided I have the mechanism that I've put in the system for it to transform to monosulfate or monocarbonate later on. It can be either. It could be monosulfate or monocarbonate, which can transform and make it stable. Okay. Any questions on this? All of you good with this so far? Basic concepts. I think Dr. Das was telling me that I'll have to give you the notes at the end. So I'll give you an entire PDF of maybe 1,000 slides, which you can study for the rest of your time whenever you want it, and you can go back and refer to it when you need it. Okay. So now, if you do that equation and just do a derivative with respect to radius and equate that derivative to 0, you get the critical radius as a function of surface free energy and volume free energy. Very simple equation. Tell me what the surface free energy of a certain particle is. Tell me what the volume free energy of a certain particle is. I'll tell you what size you need for it to grow into a larger nucleus. Okay, and that's the value of that. And using that, you find out your Gibbs free energy. One very important thing here with Gibbs free energy, and this is something Gibbs free energy is proportional to the cube of what? Surface free energy, and inversely proportional to the square of the volume free energy. Now, that gives you every theory. That's the theory behind everything that somebody tells you when you make cement for high strength. What does it tell you? Proportional to the cube of the surface free energy. How can you increase the surface free energy? By increasing the surface area, right? Surface free energy is a function of surface area. How do you increase surface area? By reducing the size of particles, by grinding more. How do you get a high strength cement? That is where the entire theory is. You get a higher critical radius, you increase the formation of a higher size of critical radius of the particle, which means you increase the reaction rate just by increasing the surface area. So everything that somebody has told you, oh, increase the surface area, rate of reaction will be faster. This is the fundamental particle level proof of that. Right? The change in free energy or the critical free energy is proportional to the cube of surface free energy and inversely proportional to the square of the volume free energy, which means if you make the particles smaller and smaller, surface area increases, so that cube, this one goes up, and when you reduce the particle size by grinding, volume comes down, right? Volume of an individual particle comes down. Therefore, this value comes down. Effectively, that increases, right? So, by just reducing the surface area, you bump this up, you bump this down.